Hello everyone, welcome to this lecture. In the last 3 lectures, we studied frequency domain representation of continuous and discrete signals of periodic and aperiodic types. We saw that how discretization is done and how the frequency domain representation of the discrete signal is obtained by a discrete Fourier transform. The discretization of the signal and digital processing of the signal may be associated with some errors. Though these errors can be avoided or reduced. So, in this lecture today we are going to talk about 2 of the errors which may be associated with digital signal processing, and we will also look at how these errors can be avoided or reduced. So, a brief outline of the lecture is as follows. First we will look at what is aliasing. I will first discuss that how time sampling of a continuous signal affects the frequency domain representation of the signal and our ability to retrieve the frequency domain representation of the continuous signal from the Fourier transform of the sampled signal. We will see that what is Nyquist sampling theorem, then we will also look at an example of aliasing, and then we will see that how aliasing can be avoided, what measures can be taken to avoid aliasing. Then we will talk about quantization noise. What is quantization, how quantization is done, on what factors the quantization error depends, and then also we will look at an example to see that how the input voltage range used for measurement affects quantization error. Okay. So, this is briefly the outline of the lecture. So, let me formally write down the topic today, which is aliasing and quantization error in discrete and digital signal processing. So, to understand what is aliasing, okay, let us first see that what is the effect of time sampling, okay, of the continuous signal on the frequency domain representation of the sampled signal. So, we are first going to study effect of time sampling on the frequency domain representation of the sampled signal. Okay. So, let us consider an aperiodic signal. Let us say we have this aperiodic signal, the continuous aperiodic signal, which is to be measured and analyzed, right. So, let us represent this by xc. So, c is the subscript for continuous signal. Okay. So, the process of time sampling can be looked upon as product of this continuous signal by a signal which consists of a train of unit impulses. Okay. So, I can show that here through a figure. So, like this. So, this is a signal which is a train of unit impulses. Is going up to minus plus infinity, and then on the negative frequency side also we have these unit impulses like this going to the minus infinity. So, let us represent this signal by St, right, which is the sampling signal, and let us say this time interval between 2 consecutive unit impulses be delta t. Okay. So, this S of t basically consists of a sequence of Dirac delta function, and we have studied what is Dirac delta function in the earlier classes, right. It represents a unit impulse. So, therefore, if this x of c, the signal to be measured, the continuous signal to be measured, if it is multiplied by s of t, okay. Then we get a signal, right. Let us show the signal that we obtain after multiplication. So, that signal we are going to represent by xs, where subscript s represents the sampled nature of the signal. So, here basically the signal s of t will be modulated by the continuous signal. The amplitude of the x of xc basically modulates this signal, and this signal will be of this form. Like this. So, if I just try to show it like this, then something like this. So, this is nothing but a sampled signal. So, mathematically therefore, we can write down x s, which is now a sampled sequence or a sampled signal, and delta t, right, is equal to x c t multiplied by s of t, right. So, here delta t is nothing but the sampling interval, okay, and that basically is related to the sampling frequency by this relationship, f of s is equal to 1 by delta t, and the sampling frequency in radians per second will be nothing but twice by f s. So, this is basically how the sampling is carried out, and this is how mathematically the sampling can be viewed at. It is basically product of a signal s of t, which consists of a train of unit impulses, okay, and that is multiplied to the continuous signal to be measured. So, when this is done, what we get at the end of it is a discrete signal, right. So, x of s is a it is a discrete signal or sampled signal. So, in order to study what is the effect of this sampling on the Fourier transform or frequency domain representation of the sampled signal, let us take the Fourier transform of this equation. Let us go to next page. So, taking Fourier transform, right, and let us represent the Fourier transform by uppercase or capital letters, right, and we know that when two signals are multiplied in the time domain, in the frequency domain their corresponding Fourier transforms get convolved, okay. So, frequency time domain multiplication corresponds to frequency domain convolution, and we can write this as x s omega, which is nothing but the Fourier transform of the sampled signal, and this would be equal to 1 upon 2 pi into the Fourier transform of the continuous signal, right, and then its convolution with the Fourier transform of the sampled signal s omega, okay. So, this is nothing but the convolution operation. So, to obtain x s omega, which is nothing but the Fourier transform of the sampled signal, we need to first of all find the Fourier transform of the signal s t, which is the train of unit impulses, and after that we need to take convolution of that with respect to x c omega, which is the Fourier transform of the continuous signal. So, when these processes are followed, then we get basically the x s omega, and it can be shown that x s omega is given by 1 upon delta t summation x c omega minus k omega s, okay, with k varying from minus infinity to plus infinity. So, therefore, x s omega basically consists of summation of basically the x c omega and the copies of the scaled version of x c omega shifted by the frequency k into omega s, where k varies from minus infinity to plus infinity. So, we can to get inside, we can expand the right hand side, and we can write that as plus x c omega plus 2 omega s plus x c omega plus omega s, right, plus x c omega plus x c omega minus omega s plus x c omega minus 2 omega s, right, plus in this way it goes up to value of k going up to plus infinity. So therefore we see here that xc excess omega consists of the scaled values of xc omega and its shifted version, where the shifting of the xc omega is given by quantity k omega s. Therefore we see that excess omega is periodic. So excess omega is periodic, and periodicity is equal to omega s, that is the sampling frequency. So to get better idea, let us try to sketch excess omega. Okay, let us go to next page. So here we have xc omega, and let us say it is something like this. Okay, so the bandwidth of xc omega is omega h. So this spectrum we are showing on the positive and negative frequency. So omega h is the highest frequency component present in the signal. Okay, that is the highest frequency component. And now what is x omega? That would be this. So here now we are showing x s, that is the frequency domain representation of the sample signal. And now this is going to be a sum of xc omega. So this is 1 upon delta t, right, 1 upon delta t, and so this is the first term, that is xc omega, and then we have the term xc omega minus omega s, which means that xc omega is shifted by frequency omega is equal to omega s. So this that appears at frequency omega s, centered at omega s. Then we have the term xc omega minus 2 omega s, which is nothing but the xc omega shifted by omega equal to 2 omega s. So we have another copy of xc omega located at 2 omega s. Okay, in this way we have copies going up to infinity. So on the negative frequency side also we have xc omega plus omega s, which is nothing but xc omega located at minus omega s, and then we also have a copy xc omega plus 2 omega s, which is nothing but xc omega located at omega is equal to minus 2 omega s. In this way here also it goes up to minus infinity. So this is nothing but excess omega. So therefore it is easy to see from here that excess omega is periodic, okay, and this is the periodicity from 0 to omega s or omega minus omega s by 2 to omega s by 2, that also can be considered as one period of this excess omega. So this basically explains us that what is the effect of time sampling on the frequency domain representation of the sampled signal, okay, and the conclusion is that the frequency domain representation of the sampled signal is basically is periodic, and it consists of copies of xc omega repeated, right, and shifted by amount k into omega s, with k being the integer and varying from minus infinity to plus infinity. Let us now try to understand that this periodicity of excess omega, does it affect our ability to retrieve the spectrum of the continuous signal from the the spectrum or the Fourier transform of the sample signal. Okay. So, is it possible to retrieve and determine the spectrum of the continuous signal from the spectrum we got for the sample signal? Let us try to answer this question, right. So, here therefore, we are going to study the or we are going to answer the question that can we determine the spectrum or Fourier transform or frequency domain representation of the continuous signal, which is the original signal we are trying to analyze, from the Fourier transform or spectrum of the corresponding sampled signal. Okay. So, that is the question. To see this, let us look at this figure again on the left hand side, and let us say this point at the origin, let us call this as O point, let us call this point as point A, and let us say this point here, let us call it B. So, let us now consider the case when let distance OA is more than OB. Also, we should know that the OA distance, what is OA distance? That is nothing but omega s minus omega h, right, because I think we can also write that here, that this frequency, right, this frequency here, this frequency is omega h, right, and therefore, OA distance would be nothing but omega s minus omega h, right, and OB distance is nothing but omega h, right. So, when which also can be written as omega s is more than twice omega h, right. So, when this is satisfied, which is basically is there in the present case as shown in the figure, then we see that the successive copies of the xc in the spectrum xs omega, they do not overlap, right. The periodic copies of xc omega, they do not overlap. So, observation is that the copies of xc omega do not overlap in the spectrum xs omega, they are separated. Okay. And if that is the case, then we can use a low pass filter, okay, whose cutoff frequency is chosen such that the cutoff frequency is more than omega h and it is less than omega s minus omega h. So, if you use a low pass filter with the cutoff frequency given by that expression, then we can filter this sampled signal and obtain the filtered signal, which basically would describe the the frequency domain representation of the continuous signal. So, let us now use a low pass filter to filter the signal, and let us say the filter is given by let us say this is the filter whose frequency response is like this. So, this is the filter H whose magnitude is shown here, this is the frequency. So, this is a ideal low pass filter. So, this filter is ideal because its frequency domain has a sharp cutoff. Frequency domain has a sharp cutoff. This is the frequency omega c, which is the cutoff frequency of the filter. Okay. So, this filter allows only the frequency components which are inside this range omega c and minus omega c. In this range the frequency components are allowed to pass through, while all the rest of the components are truncated. Okay. So, when this filter is used and then signal the sample signal is filtered using this filter, then what is the frequency spectrum of the filter signal? Let us show that here now, the frequency spectrum of the filtered signal. So, this is nothing but, let us call that as XSF, that is the filtered sample signal. So, because the filter characteristics are ideal, and let us say this magnitude of the filter is 1 here, right. So, what is going to happen? Only the copy Xc omega will be retained in the filtered signal. Okay. So, only the copy Xc omega, which will be like this, it will be retained in the filtered signal. And then we compare, when we compare XSF, okay, omega with Xc omega, then we see that there is only a difference of scaling factor 1 by delta t. So, if we appropriately scale XSF, okay, by the factor, by dividing it by 1 upon delta t, then basically we get the the Fourier transform of the continuous signal, right. So, also we should note that let us say Xc omega, the magnitude is 1 here, right. So, therefore, the conclusion is that the filtered spectrum, right, or the spectrum of the filtered signal Xc omega, it basically, if we divide this by 1 by delta t, okay, then that basically is found to be same as spectrum Xc omega. So, in this way we can retrieve the spectrum of the continuous signal from the spectrum of the sample signal by using a low pass filter. So, this is something has been possible when omega s is more than 2 omega h. The sampling frequency of the signal at which the signal was sampled, that sampling frequency, when it is more than 2 omega h, then the retrieval of the spectrum of the continuous signal from the spectrum of the sample signal is possible. Let us see in another case where this condition is not satisfied. Let us go to the next page. So, let us say that the case B, if OA is less than OB, okay, which basically means that omega s minus omega h is less than omega h, or omega s is less than twice omega h. So, let us try to sketch the spectrum x s omega again. So, let us sketch that. Omega. So, here we are sketching. So, this is the first copy of the signal, okay. So, this is at omega h, and this is minus omega h, and this is 1 upon delta t. So, the next copy of the signal would be basically like this, okay, here, and this is located at omega s, and then the omega plus omega minus 2 omega s will be somewhere here like this. So, this is at 2 omega s, and then this will continue up to plus infinity. So, on this side also what is going to happen is that there will be overlap like this, okay, and this is nothing but minus omega s, and then we have omega plus 2 omega s, which will be located at minus 2 omega s, okay, and then this will continue here like this. So, what we see that now the copies of Xc, they overlap in XS omega, right. So, let us try to show the resultant spectrum so now what is going to happen? We will have the magnitudes getting combined in this manner, okay, like this. So wherever the overlap is there, the successive copies, the adjacent copies, their magnitude gets added like this. So on this side also the same thing happens, the magnitudes get combined like this. Okay, and so if we see this frequency, so this of course is omega s, okay, and this is 0, this is minus omega s, so on. So now if you try to use the low pass filter again here to retrieve the signal, let us again sketch the filter here as we used in the previous case. So this is the filter, okay. So this is the cutoff frequency of the filter. So what kind of spectrum would be there for the filter signal? If we sketch that here, then so now it is going to be a spectrum like this, right. So let us say this omega c is if we take equal to omega s by 2, right, and omega, so what is going to happen? So this is basically the frequency omega s by 2, that is the one period of the basically xs omega, okay. So this is nothing but spectrum XSF, right. So therefore what is the conclusion? That the copies of xc, they overlap in xs omega, and the spectrum XSF, right, it is seen that it is no longer same as xc omega, it is distorted, okay, it is distorted, especially the high frequency components, they are getting distorted, and this distortion of the signal basically is referred as aliasing, okay. So distortion of the signal is referred as aliasing, okay. So therefore if you see the time domain signal xs t, then we would see that no longer matches with the original signal, or that does not represent the original signal, continuous signal well. And this aliasing occurs because omega s is less than twice of omega h, right. The sampling frequency is less than twice of the highest frequency component in the signal, and this basically essentially forms the statement of the Nyquist sampling theorem. So let us go to next page. So what is Nyquist sampling theorem? So Nyquist sampling theorem states that the sampling frequency should be chosen such that it is more than or equal to twice the highest frequency component present in the signal. So omega s should be more than or equal to twice the highest frequency component present in the signal, okay, and this has to be done to avoid aliasing. Okay, this has to be done to avoid aliasing. Let us consider an example to get further insight into why aliasing occurs. So let us take example of a cosine wave. So let us take example, and let us say we have a cosine wave xct is equal to 1 cos 2 pi f naught t, right, with f naught is equal to 5 hertz. So, it is a 5 hertz signal, and let us say we measure 1 second length of the signal. So, t is equal to 1 second. Let us now sketch the signal. So, this will signal will complete 5 cycles in 1 second. So, we have 2, 3, 4 and 5, and then these are the middle points of each cycle. And now let us sketch the signal like this. So, this is 0 and this is 1 second. Let us now use a sampling frequency of 12 hertz to sample the signal. So, let Fs is equal to 12 hertz. So, with this sampling frequency there will be 12 samples in 1 second. Let us now discretize the signal using this sampling frequency, and let us sketch the discrete signal. So, we have this like this, and then we have first sample here, then we have a sample here, okay, and then we have a sample here somewhere, then we have sample here, then we have sample here, then here, then here, right, and then we have sample here, 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 and here, and here, right. So, these are the 12 samples we have got, okay, and let us now to try to reconstruct the signal using these samples. So, we can do that by joining these samples by smooth curve. So, let us join it by smooth curve like this. Right, and then the first sample of the next cycle would be here. So, therefore, if we connect that, then we get this signal, okay. And so, what we see that the reconstructed signal is representing the original continuous signal well. It is able to capture the variations which are occurring in the continuous signal, and in fact, the frequency of this reconstructed signal is 5 hertz, and this matches with the frequency of the continuous signal, that is 5 hertz. And in fact, if we see the sampling theorem, then that is also satisfied by the sampling frequency, because the sampling frequency is 12 hertz, which is basically more than twice the sampling twice the frequency of the signal, which is 5 hertz. And therefore, in this case there is no aliasing, there is no aliasing, because the frequency inferred from the discrete signal is correct. Let us now take a sampling frequency of say 6 hertz. So, in this case there will be 6 number of samples, and let us now sketch the discrete signal, okay. So, in this case these are 2 samples, and then we have one sample here and another sample here, and we have one sample here and another sample here. So, this makes 6 samples, right, and let us try to reconstruct the signal based on this discrete samples. Let us join the samples by smooth curve. Okay, so these are 6 samples, and then the first sample of the next period also we can join. So if we join the first sample, then this is here. So what is the observation? The reconstructed signal does not follow the variations in the continuous signal. Okay, so there are 5 cycles in the 1 second length of the continuous signal, but here we have only 1 cycle, right? And therefore, the frequency predicted by the reconstructed signal is just 1 hertz. The frequency predicted is 1 hertz. So this means that the original signal, which has frequency of 5 hertz, is being misinterpreted as a signal with lower frequency, that is 1 hertz. Okay, and this is basically aliasing. Okay, so there is aliasing. And this is also confirmed by the sampling theorem, because the sampling frequency of 6 hertz does not satisfy the sampling theorem. So it can also be shown that the frequency of the Alias signal, okay, is given by Fs minus F naught. So if there is aliasing, the frequency of the Alias component will be Fs minus F naught. So which in this case is 6 hertz is the sampling frequency, and the true frequency was 5 hertz, and therefore the frequency of the Alias component will be 1 hertz. And that is what we see from the reconstructed signal. How aliasing can be avoided. So, so one straightforward way of avoiding aliasing is by satisfying the sampling theorem, right? That is by choosing the sampling frequency such that the sampling such that the sampling theorem is satisfied. So that is the straightforward way that satisfy the sampling theorem. Okay, which basically means that choose the sampling frequency omega s such that it is more than or equal to twice the highest frequency component present in the signal, right? So omega h is the highest frequency component. So that choice can be made only when we know what is the highest frequency component in the signal, right? And then often this omega h or the highest frequency component is not known, and therefore we cannot basically choose the omega s in this manner, right? Can we use DFT to know what is the highest frequency component in the signal? Can we take a discrete Fourier transform to know the highest frequency in the signal? We can't do that, because for discrete Fourier transform we need the discrete signal, and to obtain discrete signal we need to choose sampling frequency, right? So if we use some arbitrary value of the sampling frequency to obtain the discrete Fourier transform, then we may not be sure whether the aliasing has occurred or not. That would depend on the frequency content of the signal, right? So therefore we can't use DFT to find the highest frequency component in the signal, for the purpose of choosing the sampling frequency, satisfying the sampling theorem. Therefore when the highest frequency component is not known, the approach that is used is to use what is called as an anti-aliasing filter. So we use an anti-aliasing filter. So what is an anti-aliasing filter? Anti-aliasing filter, we can abbreviate that as AAF, is an analog filter. So AAF is an analog filter. Okay, so the signal is filtered. The analog signal we are trying to measure is first filtered by this filter. Okay, and its output is again an analog signal. Okay, so let us represent the process in this manner, that we have the signal XCT which we want to measure. So that is passed through an anti-aliasing filter AAF. Okay, and Now, this requires the selection of some cutoff frequency, let us call that as omega c, the cutoff frequency of the filter. Okay. And so, this cutoff frequency depends upon that what is the frequency range of measurement, in what range we want to measure the signal. This point we will discuss more later in one of the lectures. So, when this is done, we get a filtered signal, let us call it XFT. Okay. So, when we get a filtered signal which again is analog, and now we basically measure the signal, right, and therefore, there would be an analog to digital converter here, which will basically do the discretization of the signal, okay, and convert it to a digital signal. Let us call it XN, right. So, this basically gives us a discrete signal. So, therefore, this anti-aliasing filter is an analog filter, and then all the frequency components which are beyond the cutoff frequency omega c, they are simply removed, right, from the signal, right. So, XFT contains only the frequency components up to omega c. XFT contains frequency component only up to omega c, and once we know that now there are no frequency components beyond omega c, then we can choose the sampling frequency as per the sampling theorem, ensuring that the sampling frequency is more than or equal to twice of omega c. So, in this manner we can avoid aliasing. Okay. So, in in the commercial analyzers, FFT analyzers, this anti-aliasing filter is a built-in filter. Okay, it is built into the analyzer, and depending upon the frequency range you choose for measurement, the anti-aliasing filter cutoff frequency is automatically chosen to ensure that there is no aliasing. Okay. But if we are using any laboratory made setup for measurement data equation, then we may have to use an external low pass filter before the the end of the ADC, right, to remove the high frequency components and to avoid aliasing. Let us now talk about what is quantization error. Okay. So, let us first understand what is quantization. So, what is signal quantization? How quantization is done? Quantization is basically done by A to D converter, right. So, we can represent the process in this manner, that we have this the signal XCT, right, which is the continuous signal we are trying to analyze. Okay. And then of course, we have anti-aliasing filter, okay, which basically gives the filtered signal, and then after that it is sent to so let me show that here, anti-aliasing filter, which basically gives a filtered signal, okay, and then the signal is now sent to A to D converter, in which the first step is the step of discretization. So, we have discretization is the first step, okay, and then after that the signal is discretized, then it is quantized. So, we have quantization, okay. So, we have here the discrete signal is xn, and then we do the quantization. So, let us call it as xqn, right, and then the signal is converted to a digital signal by binary coding, okay. So, this basically gives us a digital signal xdn. So this all these three processes basically are carried out by A to D converter, right. This is AD converter, okay. So, therefore, when the discretization is done, the discretization is based on discrete time instants, okay. Some sampling interval delta t is taken, and then the signal is discretized. So, then it leads to discrete time instants, but the amplitude of the signal is still continuous, okay. The amplitude of the signal is still continuous. So, amplitude of xn is continuous. So, quantization basically discretizes the amplitude of the continuous signal. Okay. The quantization process discretizes the amplitude of the signal. So, to carry out quantization, basically certain number of ranges of the signal amplitude, they are fixed, called as quantums or quantization intervals. So, certain number of quantization intervals are fixed, and then the signal amplitude at each sample, okay, at each instant, the signal amplitude of each sample is rounded up to the quantization interval which is nearest. Okay. So, in this way each sample amplitude is associated or is converted to a particular quantization level, and that completes the process of quantization. So, if we have let us say n bits of A to D converter, which we can abbreviate as ADC, right, then we will have 2 to the power n number of quantization intervals. Okay. So, the number of quantization intervals would be 2 to the power n. Okay. And then what would be the width of the quantization interval? So, let us go to next page. So, the width of the quantization interval which we can represent by delta V, that depends on what is the maximum voltage range that can be measured, right, what range we want to measure. So, if let us say we want to measure plus minus V max voltage range, then twice of V max is the total range which needs to be quantized, that divided by the number of quantization intervals, that is 2 to the power n. Okay. So, that basically gives us the width of each quantization interval. So, we can also show it by figure, that let us say the maximum voltage range that we want to measure is, that is the plus V max and up to minus V max. So, that is the maximum range of voltage that can be accepted by A to D converter. So, signal to be measured must be within this range, and this range needs to be chosen for measurement to be taken. So, if V max and minus V max is the upper and lower limit of the voltages that can be measured, then the total length of the range of the voltage measurement is twice V max, and this range is to be now divided into a finite number of quantums, right, and the number of those intervals are 2 to the power n, and therefore, the width of each interval is nothing but delta V, which is given by twice V max upon 2 to the power n. So, how now quantization is done? How quantization is done? So, let us try to understand how quantization is done through a through an example, right. Let us take example where number of beats is equal to 3. Okay. So, there are 3 bits in the A to D converter. Of course, in the practice the number of beats is much more. For example, a typical analyzer may have something like 24 bits, right. So, that is very large, but for purpose of discussion let us take number of bits to be 3. So, in that case the number of intervals would be 2 to the power n would be 8, there would be 8 intervals, right. And so, let us try to sketch a figure to see that how quantization is done. So, on the x axis let us mark the quantization interval. So, there are 8 intervals. So, 4 intervals on the positive voltage side and 4 intervals on the negative voltage side. So, we have let us say this is delta V, then we have 2 delta V, then we have 3 delta V, and then 4 delta V. So, there are 4 intervals here, and then on the negative side also we have minus delta V, minus 2 delta V, minus 3 delta V, and minus 4 delta V. Okay. So, now the signal amplitude at any for any sample will lie in one of these intervals. So, we will have signal, discrete signal here, that is xn, right. And now depending upon in which interval it is, a quantization level is associated with that interval, and the quantization level for each interval is equal to the average value of the signal in that interval. So, therefore, in the first interval the average value of the signal is 0 plus delta V upon 2, that is delta V by 2, and therefore, the corresponding quantization level which is shown on the y axis. So, for any signal sample which is in this range, the signal quantization level would be this. So, this is nothing but delta V by 2. If the signal is in the second range, that is from delta V to 2 delta V, the quantization level for this any sample in this range would be an average of the two values, that is delta V plus 2 delta V upon 2, that is the 3 delta V by 2. So, the signal amplitude would be basically this for that sample, and therefore, this is nothing but 3 delta V upon 2, right. If the signal is in from 2 delta V to 3 delta V, the signal amplitude would be equal to 5 delta V upon 2, and then we will have signal any sample in the range 3 delta V to 4 delta V, the quantization level would be basically 7 delta V upon 2, right. And similarly, on the other side, from 0 to minus delta V, the signal amplitude would be minus delta V upon 2, and then you have minus 3 delta V upon 2, and then you have minus 5 delta V upon 2, and then we have minus 7 delta V upon 2. So, therefore, on the y axis what you got is the quantized signal, q subscript representing the quantized nature of the signal. So, how quantization would be done for any sample, right, xn, that we can mark on the x axis, and then we can read the corresponding quantization level from the x axis, and that would give us basically the quantized signal xq. So, once quantized signal is obtained, now this is converted to a digital form, right, through binary coding. So, if we have the quantized signal say xq and here, so let us say the different levels are minus 7 delta V by 2, then minus 5 delta V by 2, then minus 3 delta V by 2, then minus delta V by 2, then we have delta V by 2, then 3 delta V by 2, 5 delta V by 2, and 7 delta V by 2. Okay. So, let us say this is the these are the different quantized levels. So, now each level is then converted to a binary equivalent, let us call it xdn, right. And so, therefore, now this is 1 0 0, okay, this is 1 0 1, this is 1 1 0, and this is 1 1 1. Then we have 0 0 0, then we have 0 0 1, 0 1 0, and 0 1 1. So, this basically gives us the digital signal like this. Okay. So, from xq we obtain xd, and then it is the signal xd that is processed by the DSP processor to find the DFT. So, this quantization, we see that it basically causes some distortion of the signal, because the signal amplitude is basically rounded off to the nearest quantization interval, and the corresponding quantization level then basically represents the signal amplitude for that sample, and therefore this introduces some small error in the amplitudes of different samples. So therefore there is something what is called as quantization error or noise. So quantization error, also referred as quantization noise, is basically the difference of, if we represent a quantization error by En, then it is nothing but the difference of xqn and a discrete signal xn. Okay. And this En basically would be in the limit delta V by 2 to minus delta V by 2. So the range of this E would be basically governed by the width of the quantization interval. So higher the width of the quantization interval, higher it is likely to be the quantization error, right? And definitely we would like to keep the quantization error as small as possible. So, but on what factors the quantization error depends, right? The factors that affect quantization error. So the first is that the number of beats of ADC, okay, number of beats in the ADC. So higher the number of beats, lower would be the quantization error. So higher the number of beats, that is n, okay, smaller would be the error, basically quantization. Because if n is higher, the number of intervals becomes larger, and then the width of each interval, quantization interval, becomes smaller, and therefore the quantization error also would be correspondingly small, right? The rounding up error would be smaller. The other factor which affects quantization error is what is the range of voltage measurement, right? And that depends upon the maximum voltage on positive and negative side, that basically is to be measured. So therefore Vmax also affects quantization error. Okay. To understand how Vmax affects, let us take a simple example. Let us go to next page and let us take an example. Okay. So let Vmax is, let us suppose, 10 volts. So this Vmax is to be decided before a measurement is taken, that what is the maximum voltage that we expect the signal to have, right? So based on that, this maximum voltage range has to be decided before the measurement, and let us say we have taken Vmax as 10 volts. So let us show that here. So let us say this is the 10 volt Vmax. Okay. Now let us consider first case where the signal amplitude is, let us consider signal amplitude, okay, to be of say 9 volts, which means that we have a, let us say, signal xc is equal to 9 cos, let us say, 2 pi 1 t. So it is a 1 hertz signal with 9 volt as its amplitude. So this signal would be basically appearing like this. Okay, something like this. So this voltage range is 9 volt, while Vmax we already know it is 10 volts, right? So therefore when this signal is quantized, this signal is likely to appear in this form after quantization. So, this is likely to be approximately is going to be the nature of the quantized signal, like this. Okay. And what we see, the quantized signal which is xq, right, that closely follows the continuous signal, right. So, the quantization error is not much. Let us say we have another signal now, let us call this xc1, let us call it xc2, and this signal is, let us suppose it is a 3 volt signal cos 2 pi 1 t. Okay. And let us try to sketch what is going to happen to the quantization in this case. So, this is the voltage range V max. Okay. This is 10 volts minus 10 volts, and the signal is something like this, something like this. So, this is 3 volts, and what kind of quantization it is likely to lead to, you know, it may have okay. So, this is how the quantized signal is likely to look like. So, here what is going to happen, the signal amplitude is you know, much less than the signal we want to measure, than the maximum voltage that is permissible, and therefore, the quantization error is much larger. Okay. The quantized signal does not follow or represent the shape of the continuous signal accurately. So, we have a large quantization error here. So, quantization error is large, okay, because most of the signal amplitudes would be basically rounded up to first few quantization intervals, right, and other quantization intervals basically are not utilized for signal discretization. So, that is why the choice of, you know, the maximum voltage here is not optimum. The 10 volt is much higher than 3 volt. A better, you know, maximum voltage would have been somewhat more than the 3 volt, you know, signal level. Let us take another example. Let us take another signal xc3, and let us say the level here is, let us say 12, signal is 12 volt cos 2 pi 1 t, right, and let us try to sketch what kind of, you know, quantization this would result to. So, let us say this is 10 volts minus 10 volts, okay, and let us sketch the signal here now. Now, the signal amplitude is more than 10 volts, something like this. Something like that, right. And now, how quantization is going to happen? We may have a sample here like this, sample here like this, and now here the signal would be clipped because it exceeds the signal amplitude for these samples, it exceeds the maximum allowable range, right, and then the signal like this. In this manner. So, what is going to happen? It is going to cause clipping of the signal. Okay. Here also we have clipping. So, whenever the signal amplitude exceeds the maximum voltage range, the signal is clipped, and this leads to a severe distortion of the signal. Okay. So that also has to be avoided. So this basically leads to severe distortion of the signal due to clipping and should be avoided. So such a measurement basically should be rejected because it's not, does not form a proper measurement. Okay, the such as situation is to be avoided. So analyzers typically indicate the presence of higher voltages than the maximum allowed by an overlaid indicator. So there would be an overload indicator, okay, in the analyzers, which would show that the signal is basically the ADC is being overloaded by the incoming signal, right. So when such an indication is given, that measurement should be not be accepted. So therefore Vmax should be optimally chosen, and ideally it should be just little bit more than the signal that we want to measure, okay. So that would give us minimum quantization error. So in many cases it may not, the signal may be fluctuating, right. The signal level might be fluctuating from a very high value to a very low value, and therefore in such cases it may not be easy to choose a value of Vmax. So to deal with such situations, the analyzer also contains an option of what is called as auto range option, right. There is something called auto range option in most signal analyzers. So when this auto range option is active, right, and when it is chosen, then the analyzer automatically chooses the Vmax or the maximum voltage that should be measured, right, that is permissible, and then it keeps on checking periodically the signal level and keeps on revising the value of Vmax, right. So that helps to us to basically choose Vmax and keep the quantization error small. So in this way, in the lecture today we discussed two sources of errors in digital signal processing and discretization, right, and this basically completes our discussion today. We can stop here. Thank you.